Great. So next up we have Zhaozhou Li from the Hebrew University of Jerusalem.
Hi everyone. Good morning. I'm Zhaozhou Li. It's a great pleasure to present our understanding on the early galaxy formation. In previous talks, people have talked about the observation and the simulation side. Then here we would like to mention more about the theoretical side. Let's start with the star formation efficiency. So in our general common understanding, the galaxy formation is not an efficient process. We define the star formation efficiency as the ratio between the stellar mass over the available baryonic mass within the halo. And this efficiency is typically low, especially at low redshift because of the feedback. For example, by supernova feedback at low mass end and aging feedback at high massive end. However, recently JWST observation proposed us a question: what's the expectation for massive galaxies at high redshift, like redshift 10? Here we propose that such massive galaxies at high redshift are expected to have high star formation efficiency by the feedback-free starburst, which is a robust prediction from the first principle for high density and low mentalisity gas clouds, which is common at high redshift. This plot shows you, give you a basic idea. Here, this plot shows the mechanical power of feedback from a starburst. So for a single stellar population, we have the supernova burst after 3 million years from the star formation. And then we have a time window before the stellar wind becomes too strong, a window of about 2 million years for when the mentalisity is low. So that's to say, if the gas clump can collapse fast enough, then the star formation can go largely in a feedback-free way. And we can turn this critical time scale into a density scale. As we know, for when the density of a gas cloud is higher, then the collapse time is shorter. Then we basically have a if the density is high enough, then the system collapses fast. But this is not the end. We have to consider other processes. For example, the gas cloud must cool fast enough in the time scale of collapsing. So this requires a high density of the gas cloud and a minimum mentalisity for efficient cooling. Also, the gas cloud should be self-shifted from the supernova wind from the earlier burst. And luckily, all these criteria are satisfied when the gas cloud density is above certain threshold, 3,000 per centimeter cube. And similarly, we also have to consider that the gravity should be stronger than the radiative feedback, which leads to a threshold in the surface density. We have discussed these microscopic conditions for gas clouds, for gas clumps, and by with model we estimate the conditions and we turn it into an estimate of the threshold of halo mass. So for it's about 10 to 11 solar mass at redshift 10, and the threshold is lower at high redshift. So below this critical halo mass, we are in the standard region and suffer from the feedback. And above this, we will have the high star formation efficiency in a feedback-free way. What does FFB galaxy look like in general? Here I show you a picture. For those high massive halos at high redshift, we expect efficient cold inflow via the gas filament. And this cold flow will encounter the supernova wind from the earlier generation of stars. So they will form a shock here with enhanced density. As the density is high enough in this condition, and it reaches the instability, and will form a new generation of stars largely in a feedback-free way for gas clamp of mass 10 to 6 solar mass. And we are verifying this picture with simulation. Also, similar scenario can be applied when the infalling gas streams have some non-zero angular momentum. Then the gas will fall into a gas disk. As the gas accumulates with high density high enough and reach its instability, then a new generation of star can form. So, so in this scenario, we expect FFP galaxy as a compact assembly of like 10,000 stellar cluster objects within a very small radius. And this may have very many interesting implications, because these clusters can be the origin of the globular clusters that we observed at later epochs. And also these clusters can state the seed for black holes, for supermassive black holes, which I will talk about more tomorrow, and may have implications in reionization. As just mentioned, such a FFP galaxy can have, we expect multiple FFP generations. So for each generation, the star formation goes faster in the free-fall time, like about within 2 million years. And after this, it will be followed by quite relative quiescent region period, because of the faster consumption of gas and the feedback from the earlier burst. As the galaxy accumulates gas, and the gas density in the galaxy becomes higher and higher, until it reaches gas instability, and starts set on a new generation of feedback-free starbursts. Also, we based on a model on the steady supernova wind solution, we can predict the expected gas distribution and its velocity in the galaxy with a very high wind velocity. And also, we based on this model, we predict the gas profile and the fraction, and also the attenuation from this model. Also, based on this scenario, we are able to estimate the size of a galaxy as the stellar wind comes out and encounter the incoming streams. Well, the wind will stall at the radius where the two balance each other, which give us an estimate of the galaxy size. Based on all those understandings, we build a toy model for the observable predictions. Here we build the model on the basis of the universe machine. So on the low mass or low redshift part, it goes back to the standard star formation efficiency as in universe machine. And while for the halos above the FFP threshold, we assign then a high star formation efficiency in terms of star formation rate. And then we follow the the growth histories of those galaxies, and then compute the cumulative efficiency. Here I show you the star formation efficiency for different redshifts and as function of halo mass. Basically, a higher efficiency for higher mass and at high redshift. With this model, we made a lot of observable predictions. Here I show you the stellar mass function. Here the gray solid curve and the dashed curve shows the modeled by a universe machine and by Starbursts, and the dashed one shows the semi-analytical result by Aaron Young. Here the orange curve is our FFT prediction with a maximum star formation efficiency of 0.2, 100%, and the blue curve shows 100% at the maximum. Clearly, the FFT prediction shows predicts higher stellar mass function than the standard model, and the difference is higher at high redshift and close at low Z. In general, we see a good consistency between the observation and the FFT prediction with 20% efficiency. Also, we may have the prediction for luminosity function. Here is an example for redshift 11. And again, we see a consistency between our model and the observation, higher than the kind of standard model. And here I show you the density of galaxies as function of redshift. Also see encouraging consistency. And then we here it shows the cosmic density of stellar mass and the star formation rate. Right. Also, we have the predictions for the galaxy size. They are compact and expected to be smaller at high redshift, about like 0.2, 0.3 kiloparsec at redshift 10. And also we have the prediction for dust attenuation, gas fraction, and the mentalisity. So it here shows some preliminary observations in comparison. And we expect more observations to further just to verify our model predictions. Here, as we mentioned, we expect the FFT galaxies to have a bursty star formation history with a peak with a star formation period of 2 mega year and the separation between them of 10 mega year. However, these values can also be slightly different. And assuming different star formation histories, this will lead to different ratios between the different indicators of star formation rate. And in principle, we can get information about the burstiness of the star formation history from such observables. This is something in progress. We are trying to incorporate the FFT scenario to semi-analytical models. Here is a very preliminary result showing the stellar mass function for the fiducial semi-analytical model and the SAM with reduced feedback during the FFT phase. And this shows higher stellar mass function for the case with the FFT, the larger difference at high scale. Okay, here is my summary. We proposed a model we believe is a robust prediction from first principle. And we made the observable predictions with available with digital forms available. You are welcome to compare with observation and simulations, and there are some more ongoing progress.
All right, thank you. All right, we have time for one question. Oh, and I saw it there first. You're in the worst seat to get a microphone to you.
Does this model require that all the different star formation sites in the galaxy get synced up with one another, or does it work if they're out of sync? So do you need different star forming clouds in different parts of the galaxies to be on the same 20 mega year clock, or can they get out of sync with one another and all the mechanisms still work?
I'm not sure if those clamps will be synchronized. The different. I'm not sure they will synchronize. So we expect then the star formation efficiency, the star formation history then will be more random and less regular, and there can be some smooth transition, not necessarily like this sharp.
Okay. All right. Great. Let's thank our speaker again, and our last one before lunch.